Can we solve the measurement problem, or has physics encountered consciousness? To understand the measurement problem, let's start with the basics. In the paper on decoherence in the measurement problem, Maximilian Schlauhauser points out the problem we have in quantum mechanics. Particles exist normally in a superposition of possibilities, described by the wave function, which basically means, as Rosenblum and Kuttner point out, that particles normally exist as several mathematical possibilities rather than one actual object, like how we experience them in reality. So how do particles go from a mathematical state of possibilities, when we are not observing, to one physical object, when we observe? Well, this is the measurement problem. It seems in the absence of observation, particles exist in a superposition of possibilities, rather than one actual thing. But when we observe them, they are not in such a state. Something happens when we look and causes this change. The wave function on its own, which describes these possibilities, is completely deterministic, but as Henry Stapp points out, it fails when an increment of knowledge occurs. Then there is a sudden jump to a reduced state, which represents the new state of knowledge. This jump involves the well-known element of quantum randomness. So something happens between these two states. As Schlauhauser points out, we are missing a mechanism of how this occurs. Thus, without supplying an additional physical process, say some collapse mechanism, or giving a suitable interpretation of such a superposition, it is not clear how to account, given the final composite state, for the definite pointer positions that are perceived as a result of an actual measurement, i.e., why do some seem to perceive the pointer to be in one position, but not in a superposition of positions? So how is it that what we observe is different than what the wave function actually describes? How is it that collapse happens to one definite state when we observe? The practical way this is carried out is through interaction with a particle or system of particles that has already collapsed. One can measure a particle with the use of a measuring apparatus and interact with it. This will cause collapse through interaction, because the state of the particle has been disturbed. This is a decoherence effect, and some argue this can fully explain collapse on its own and solve the measurement problem. However, this doesn't really solve it, because if we were to use one particle to collapse another, what was used to collapse that particle, and so on and so on? It was Niels Bohr that pointed out we cannot specify the wave function of an observed particle separately from the other particle that is used to measure it. In other words, the wave function of a particle cannot be unentangled from that of whatever is used to measure it, and so on and so on. Basically what this means is when one photon is measured by another, they entangle. If one particle measures another, it inherits part of its wave function, so to speak, and that particle, which is supposed to be measuring, cannot be fully explained without what it is measuring. So you need another measuring device to collapse that initial measuring particle to a definite state. But then you need something else to collapse that measuring apparatus as well, and so on and so on. This creates a chain of material objects in a superposition of measuring, which is known as a von Neumann chain. Since quantum laws are what truly describe all material objects, some other particle or measuring apparatus is always needed to collapse the next one in line. You keep going back until you get to something that would be non-local, outside the entire material system, which escapes this chain by not being bound by the same physical laws, and is able to cause final collapse of everything in the chain, which is argued to be a conscious observer, something beyond the material, with the ability to collapse the entire physical system. So this decoherence theory, the idea that physical interaction of particles in the environment will cause collapse without the input of a conscious observer, cannot solve the measurement problem. And advocates of decoherence theory openly admit decoherence alone cannot fully explain why there is a collapse to one definite state, or even derive the Born rule for that matter. Does decoherence solve the measurement problem? Clearly not. What decoherence tells us is that certain objects appear classical when they are observed, but what is an observation? At some stage, we still have to apply the usual probability rules of quantum theory. Claims that simultaneously the measurement problem is real and decoherence solves it are confused at best. Decoherence arises from a direct application of the quantum mechanical formalism to a description of the interaction of a physical system with its environment. By itself, decoherence is therefore neither an interpretation nor a modification of quantum mechanics. Now, why would they say this? Well, many physicists, like G. Grubel, in his paper The Quantum Measurement Problem Enhanced, have pointed out initial state environmental effects cannot explain the occurrence of definite experimental outcomes. The environment lacks the ability to choose between the possibilities of the wave function and choose one to be actual. Plus, the environment is also described by the same quantum laws and has the same problems already specified. This is why Stephen Adler says, decoherence in the absence of a detailed theory showing that it leads to stochastic outcomes with the correct properties has yet to achieve this status. Even in preferred states predictability, classicality, and the environment-induced decoherence, Zurich refers to the observer being involved in the ultimate collapse. Something beyond the physical system, not described by quantum laws, needs to initiate this final or ultimate collapse. Stephen Barr explains it like this: the observer is not totally describable by physics. If we could describe the mathematics of quantum theory, everything that happened in a measurement from beginning to end, that is, even up to the point where a definite outcome was obtained by the observer, then the mathematics would have to tell us what the definite outcome was. But this cannot be, for the mathematics of quantum theory will generally yield only probabilities. The actual definite result of the observation cannot emerge from the quantum calculation. And that says something about the process of observation, and something about the observer eludes the physical description. So what is special about a conscious observer that the environment or the measuring apparatus cannot do? Well, apart from not being described by physical laws, the observer has the ability to put the right questions into nature and yield a result. As Henry Stapp says, the observer in quantum theory does more than just read the recordings. He also chooses which questions will be put into nature, which aspect of nature his inquiry will probe. I call this important function of the observer the Heisenberg choice, to contrast it with the Dirac choice, which is the random choice on the part of nature that Dirac emphasized. According to quantum theory, the Dirac choice is a choice between alternatives that are specified by the Heisenberg choice. The observer must first specify what aspect of the system he intends to measure or probe, and then put in place an instrument that will probe that aspect. In quantum theory, it is the observer who both poses the question and recognizes the answer. Without some way of specifying what the question is, the quantum rules will not work. The quantum processes grind to a halt. The interaction chain stems back from an observer's ability to make a Heisenberg choice, which derives a random Dirac choice back from nature. This is how we get one actual outcome from the possibilities of the wave function. Only the observer has the ability to choose, give a Heisenberg choice, between possibilities. Non-conscious measuring devices cannot. John Gribben and Paul Davies say in their book, The Matter Myth, the observer plays a key role in deciding the outcome of the quantum measurements. The answers and the nature of reality depend in part on the questions asked. They were, of course, building off of Niels Bohr, who once said in reply to Einstein, "To my mind, there is no other alternative than to admit that, in the field of experience, we are dealing with individual phenomena, and that our possibilities of handling the measuring instruments allow us to make a choice between the different complementary types of phenomena we want to study. Denying the observer plays a fundamental role simply doesn't make sense, and the majority of physicists realize they have to accept this." A recent poll demonstrated that over 50% of physicists accept the observer plays a fundamental role in the application of the mathematical formalism, but then only 6% accept any physical role, which means they accept the math tells them one thing, but deny the philosophical conclusions from that math. And this really isn't justified or logical, especially if the mathematics can only make sense if the observer plays a fundamental role. Why deny the obvious conclusion that follows? Henry Stapp rightly points out why physicists deny this philosophical conclusion. It's metaphysical prejudice. Some are trying to hold to metaphysical beliefs about the world that quantum mechanics and the role of the observer challenge. One must ask whether it is really beneficial for scientists to renounce for all time the aim of trying to understand the world in which we live in order to maintain a metaphysical prejudice that arose from a theory, classical Newtonian mechanics and materialism, that is known to be fundamentally incorrect. The fundamental role of the observer is even harder to deny with the experimental confirmation of the Cauchy-Spector theorem in 2011. This shows that the outcome obtained by an experiment crucially depend on how the experiment is done, meaning we are not passive observers. Outcomes are happening based on what we input into nature. As one paper explained, the Cauchy-Spector theorem states that non-contextual theories are incompatible with quantum mechanics. Non-contextuality means that the value for an observable predicted by such a theory does not depend on the experimental context. So when we perform experiments, we are not just passively observing how nature progresses, but are actively affecting what the outcome will be by how we observe things. As they say in the New Scientist magazine, the values you obtain when you measure its properties depend on the context. So the value of property A say depends on whether you chose to measure it with property B or with property C. In other words, there is no reality independent of choice of measurement. So the Koch-Inspector theorem directly demonstrates the outcome depends on what we experimentally put into it, as Anton Zellinger says.
The Koch-Inspector theorem talks about properties of one system only. So we know that we cannot assume, to put it precisely, we know that it is wrong to assume that the features of a system which we observe in the measurement exist prior to the measurement. Not always, I mean in certain cases. So in a sense, what we perceive as reality now depends on our earlier decision what to measure, which is a very, very deep message about the nature of reality and about our role in the universe. We are not just passive observers.
Thus, the conclusion necessarily follows. The philosophical implications of the measurement problem cannot be ignored. As they say in the quantum enigma, quantum theory thus denies the existence of a physically real world independent of its observation. The measurement problem is only a problem if one cannot accept the observer plays a fundamental role in shaping physical reality. We are not passively observing the world, but actively involved. As Rosenblum and Kuttner say, physics has encountered consciousness, and our view of the universe will never be the same.